Those Space People, a podcast series of casual cosmic conversations with people working on exciting space projects.
Today we have Jonathan McDowell with us. He is an astronomer at the Harvard-Smithsonian Center of Astrophysics. And he has a background, of course, in astrophysics and has been with the Smithsonian for more than 3 decades. Welcome to the show, Jonathan.
Great to be here.
Jonathan, can you tell us what brought you into astrophysics? Of course, astronomy is super exciting for all of us, and it's probably the sexiest aspect of doing space. But what really brought you here?
Well, there's really two things. I mean, one, as I was just telling you, my dad was a physicist, and so all of my babysitters were physics graduate students, and I had no idea that any other career path was possible. I thought they just handed out PhDs when you got to a certain age. When I was 8, he did a sabbatical year. He did atomic physics, but he did a sabbatical year at NASA Goddard. So I was at NASA Goddard as an 8-year-old the year before the moon landing. That, it was all over at that point. And so, but also I had an interest in cosmology that came out of sort of philosophical, I was a bit overblown to say it for a 10-year-old, but I was wondering where we all came from, right? Sort of religious answers didn't work for me. And I read a book by Fred Hoyle on cosmology and okay, yes, this story makes sense to me and I want to know more about it. And so there's a side of me that's been driven by that, by how did the universe begin? Where are we? What is the universe? And a side of me that was driven by Apollo. I remember as a 9-year-old, the week before the landing, walking home from school in northern England. I grew up mostly in England, and looking up at the moon and going, next week, there are going to be human beings walking on another world. And that blew my mind, and it hasn't kind of unblown since then. That's really my origin story. Fascinating.
Wow. Can you talk a little bit about your work at the Smithsonian and how does your typical work week looks like?
Right. So I'm an astronomer. I work on the Chandra X-ray Observatory project. So Chandra is like the X-ray cousin of the Hubble. And so Hubble sees the boring, ordinary things in outer space, and Chandra sees things that make X-rays, which typically is when things go badly wrong. So you have supernova explosions, or matter being torn apart as it's dragged into a black hole, or things like that. And so we see all the most awesome things in space. And because the X-rays can't get through the Earth's atmosphere, we have to put our telescope above the atmosphere. So Chandra's out about 140,000 kilometers out in space, and we sit on the campus at Harvard University, and at least in non-pandemic days, and talk to it through the Deep Space Network. So I use Chandra to study black holes, supermassive black holes in galaxies, quasars. I also run a group that figures out what software is needed for the other astronomers around the world who use Chandra. So my job is to help scientists get science out of the Chandra mission and figure out what software tools we need and work with the programmers to make that happen. So that's also fun. It's really exciting to be part of a genuine space mission and to be at that cutting edge.
Can you compare and contrast how space-based telescopes and terrestrial telescopes are generally used in astronomy? What kind of astronomers use data from space-based telescopes, and who uses it from terrestrial telescopes?
That's a really good question, because when I started out in astronomy, the overhead for learning the different technologies was so high that you were either an X-ray astronomer or an optical astronomer or a radio astronomer, but it was too difficult to be multiple. And that was really holding the field back, because the objects in space don't make that division. They put out all of this stuff, right? And particularly quasars that I study put out everything from the radio to the gamma. And so the development of standard software packages, which is not unrelated to the other part of my life, is lowered the bar to entry, right? So that a lot of the instrumental stuff was abstracted out into the software packages, which meant it possible for you, instead of being a radio astronomer, to be a quasar astronomer studying quasars with all the different telescopes. And so that's more typically what people do nowadays. They're interested in a particular scientific question and use all the toys to get at it from different angles. And so although I am paid to support this X-ray astronomy mission, I've also used Hubble and I've used infrared telescopes and the ground-based telescopes. I've gone out to Arizona, which is super fun to use the telescopes on Mount Hopkins, because you're asking questions that you need all these different kinds of angles on the object to answer. And so, and even with optical telescopes, right, people don't appreciate, there are the ones that do big wide angle images for surveys. There are the ones that like the scalpels that look at some individual very faint object and take its spectrum. And so different telescopes are optimized for different tasks. And so you really have to develop a wide range of skills to really answer these questions.
So some kind of a sensor fusion is going on. And is it, how recent of a phenomenon is this sensor fusion? You know, working with different sensors, different kinds of data?
I think it started happening in the 80s and really became standard in the 2000s. It really, multi-wavelength astronomy, as we call it, was like a weird thing that some of us did in the 80s. And then if you weren't doing it by the end of the 2000s, you were really a little stick in the mud. And so yeah, so now we're much more, and it's funny because so where I work at the Center for Astrophysics, right, we have divisions, and some of them are wavelength based, like we have the high energy astrophysics division, but some of them are science based, like we have the solar, stellar, and planetary division, who are like people who like stars and planets but not galaxies, right? So that sort of reflects this evolution in the field from what instrument you're expert in to what kind of astronomical object you're interested in. And I think now, if you go to grad school in astronomy, yeah, that's what you should be doing. You should be looking at a science question. But I've also, you know, I have a little bit of, I call it ADD, astronomical deficit disorder, where I like to sort of switch around and do different things. So I've actually started off as a theorist, and I have ended up doing every observational waveband from the radio to the gamma ray at some point in my career, and every kind of object from asteroids in our solar system to the Big Bang. And so it's just, you don't put out as many papers that way, but it keeps life more interesting.
How do you pick an astronomical question, you know, a study object? You said that some people would not like to study galaxies, but only focus on stars and planets. So what's the difference here?
I mean, I find everything in astronomy interesting, okay, almost. I can't get too excited about the science of like astrochemistry of molecular clouds is interesting, but I don't want to do it because it requires chemistry, and that's complicated. And I prefer black holes, which are nice, simple objects, and just pure general relativity. That's pretty, you know. And so it's, you know, there's an aesthetic thing of what kind of math you like, what kind of science you like, but there's also, there are big questions that we're trying to answer, right? The underlying big questions are things like, how did the universe evolve? Where did the chemical elements come from? And, you know, that's one of the big answers that we got in the 20th century, is that we now understand why carbon is common and gold is rare. And it all goes back to nuclear reaction rates in stars. How cool is that? And so, you know, people get fascinated by that, or the search for life. And so a lot of the exoplanet work, right, is really cool right now and is motivated ultimately by, are we alone? And so whereas I'd be more motivated by what on earth is a black hole, and how did the universe begin, and things like that. And so that pushes me more towards the extragalactic cosmology end of the questions that we ask.
Coming back to this point about ground-based telescopes and space-based telescopes, we now have so many constellations, satellite constellations coming up that are already interfering with a lot of these observations. So do you think we will be moving more towards space-based telescopes? What challenges would that bring?
I think in a generation or two, we're going to have to. But in this generation, you know, for the next couple of decades, it's not practical to move entirely to space-based telescopes, right? Again, as I was explaining, we have hundreds of ground-based telescopes, professional ground-based telescopes that all do slightly different things. And it's 100 times more expensive to move them into space. And so it's not like, oh yeah, just give us a couple more Hubbles, right? It's no, give us 500 more Hubbles, all different designs, each of which is going to be billions, right? And so that's just not realistic in the near term. And that's why we're fighting hard to preserve some amount of the night sky for the use of astronomers and ordinary people, and not have the sky completely overrun by bright satellites. So I'm really pleased that SpaceX have stepped up to do some modifications to their system, and OneWeb have downscaled their system a bit. And so in the near term, things aren't looking as dire as they were a year ago. But in the longer term, we don't want to have to rely on the generosity and public spiritedness of big corporations. All different countries are going to be putting up these constellations, right? So there needs to be a greater level of international coordination. And just more broadly, I think this is one aspect of what I've been calling space environmentalism. There have been a lot of different issues that have come up over the past couple decades, from this light pollution issue to space debris to ionospheric modification, planetary protection, making sure we don't send bugs to Mars. And these are all different aspects of the fact that our impact on outer space, in the inner solar system at least, is starting to become significant. And we have to have a holistic environmental approach to understanding that, and an integrated kind of discussion of the space environment and human effects on it, I think is long overdue, and it's starting to come together.
The whole issue of space situational awareness, it's gaining more prominence lately.
That's like the sharp end of the pin here, is the one that's going to screw us most soon. But it's not the only one. I can't lose sight of that. But yes, and I think that, there's some encouraging developments. I think the move to move some of the SSA away from the US Department of Defense into Department of Commerce and things like that is a very positive move, because in the long run, it will make it easier for them to play with others. I think the development of a European SSA capability, a space tracking capability, is long overdue. I think they're still kind of playing around with it in a not serious enough way. As in a lot of different avenues of life, there is such potential for the EU to take world leadership, and they can't get their act together. And that's one of the things I find particularly frustrating about the 21st century, is that they're so close to being able to replace the US as the beacon of sanity in the world. And because, obviously the US has totally lost it. And instead, that's not happening. And in particular in the SSA, I think it's going too slow, and they need to invest more.
The EU definitely has a great potential to set these sort of guidelines, especially with data privacy. Recently they've set these general guidelines.
That's true. I don't agree with all of them. I think some of them are a bit too draconian. You've got to balance, especially as a historian, right? This idea that, you have to forget things. It's like, no, I don't do that. But in general, yes, I think that's right. The EU now is asserting more control of European space, and so I think that is maybe a good thing. Is it's giving it more prominence in the political arena. The formation of this European Space Authority, or whatever it's called, that will be the EU level over ESA, is I think maybe a good way to go.
There are a lot of commercial companies that are trying to get into this space situational awareness domain. There's also an American company, I guess it's called Leo Labs, and
there's Leo Labs for low orbit, and there's ExoAnalytics for the high orbit.
Yeah.
And that's right. And that's a very interesting development. And I think that is, that's great because they're much more flexible than the military, but ultimately they kind of are targeted a different space of actually the space operators, rather than the academics like me and the overall problem of space debris and space debris management, right? And I think what we're eventually going to need is a government, funded by governments, international space traffic authority of some kind that contracts to these companies to provide data, but provides a layer that is public and that everyone can use for safety of flight, and ultimately maybe for for space traffic control, instead of just warning you, oh, you guys, your satellites are about to come close to another, actually order them. Okay, this satellite go up a kilometer, this satellite go down a kilometer, and have that not be the ad hoc, up to you guys, whatever you want to do, that it is today.
So some kind of a decision-making authority that takes a call. But though we do have space laws, you can't really enforce on the international domain.
Well, at the moment, that's true. I don't think that always will be true. And I think you can, the way toward that is to establish norms, to have technical committees like the Interagency Debris Committee establish norm, to have national agencies adopt those norms. Like, don't tell me what to do, but okay, that's a good suggestion, we'll do it. And ultimately have coordinating bodies that, again, will do what this coordinating body suggests just because we think it's a good idea. And eventually that gets you to a position where everyone is doing what they're told.
We are talking about all the data monitoring, the space object tracking and monitoring and so on and so forth. So do you see these data sources, right? For example, for now, all we have is the two-line elements. Like you said, they are published by this NORAD. But the data sources, which are the ground-based radars, or perhaps in future, even space-based radars. So all this information, do you think it will just stay proprietary, either with, I don't know, the US Defense or the EU, somebody in the EU, or do you think it will turn commercial?
Well, I mean, and then the question is the commercial data, right, is going to be proprietary, even more so. So, yeah, I think that raw data level is going to stay either in the agencies or in the companies. And that there will be different levels of product that get released that are, the expensive tier with the accurate predictions and the public tier with just equivalent to the current TLEs, perhaps.
Like the GPS, for instance.
Yeah, exactly. So GPS has the civil and the military levels, right? And so you can imagine a similar sort of thing for SSA. But I think there's not going to be one source, right? I mean, already we have several. One of my pet crusades, pet hobby horses, is SSA for deep space and keeping track of what's out there in beyond geo, but also in like solar orbit and things like that, right? So right now, that data, there are no TLEs, right? So that data comes from astronomers accidentally discovering satellites when they were looking for asteroids. and from, JPL puts out the trajectories for its active probes and things like that. But there's a lot that's not being done. And so there are all these different sources of information that you have to fuse to get any sense of SSA beyond geo. Whereas, below geo, the 18th Space Control Squadron at Space Force, it's not NORAD anymore, it's Space Force, right?
Yeah.
You see, you can tell your age a little bit, right? Because I still think of it as NORAD too. But they do a great job for LEO and a decent job out to GEO. But beyond that, it's a free for all. And so I think we're starting to see some of these other sources, become more important as we have more activity in the deep space arena.
You were also previously mentioning that we need to look at this entire problem, that the space situational awareness is just the pointy edge that's going to come at us first. But there's a lot more to this entire problem of monitoring the near Earth. So do you see astronomers doing this?
I mean, we're not funded to do it is the problem, right? The guy who used to do the distant artificial satellites of the Earth page is retired now and he wasn't paid to do it. There's like 3 people doing it on their own time to take the astronomical observations that would otherwise be thrown away as not natural objects, therefore boring, and actually do something with them, right? And so there's no prospect in the near term of that becoming an actual funded activity. And I think that needs to change at some point. So radars are great for low orbit, right? But they're 1/4. If it's 10 times further away, it's 10,000 times fainter. And so for the outer stuff, you need astronomical techniques, as the DoD, the Space Force already uses telescopes to do the geo work. And so it's a natural place for the SSA and astronomy to interact.
The space now is getting more and more political. It's quite multipolar and it's really tightly being, woven into people's political agendas right now across the world. So do you see every country coming up with its own ground-based or space-based tracking facilities?
Well, I think that's unrealistic, right? And that's why I think where companies like Leo Labs may have another market is for developing country space programs to provide the ground tracking network. We're seeing also things like SatNOGs, which is the sort of more university amateur level, CubeSat tracking, sort of radio communications. So, at what level do you need your own space tracking system, right? There are the four big space powers, which are the US, China, Russia, and Western Europe. I lump Western Europe as like a country because its aerospace industry is so tightly integrated.
Yeah.
Even with Brexit. And so they're the four big ones. And then there's the second tier of India and Japan. And then there's everybody else. And I think everybody else is going to be more active in space, but they need to do it, as consortia, right? There needs to be a collaborative efforts in some of these infrastructural things. You still have your own national space program, but the infrastructure, maybe the communications, the tracking, things like that, could be contracted out and done in some collaborative way. I mean, the other thing to bear in mind, right, is I've been saying for 20 years or so, space is about 1/3 civilian, 1/3 military, and 1/3 commercial. And that was true until about last year. And in the past couple of years, the commercial sector has exponentiated. And it's clear now that what we're looking at in the 2020s is a space sector that is dominated by commercial activity and no longer by military and civilian government activity. And so that's going to put increasing strains on the outer space treaty regime where everything is a state activity, especially as you have these activities by globalized companies when it's really hard to pin them down which country they're really, associated with. And so I think we are at a point where the current regulatory environment is strained and is going to break at some point, and we're going to have to do something about that.
Yeah, when new space will actually become new space, then I think we'll have a lot of updating to do on the legal front.
Yeah, exactly.
So you've had a really long career in astronomy, right? So you've been with the Smithsonian for more than 3 decades now.
Yep, really old now. I started off in England, did a maths degree and then an astronomy PhD at the University of Cambridge. At that point, I was full up theorist doing black holes and Big Bang and things like that, and working with, my PhD advisor was one of Stephen Hawking's former students, and so I was in that gang. It was a really exciting place to be in the 1980s. And then I after a brief foray in radio astronomy at Jodrell Bank in England, I came over to the US to join the Center for Astrophysics, and then I did another postdoc at NASA Marshall in Alabama. So that was interesting. But other than that, I've been at the CFA for, as you say, about 30 years, working first as a postdoc and then as a scientist on the Einstein satellite project, and then since the mid-90s on Chandra. And so it's been a really interesting ride. I've got to be in the room I feel a little like Forrest Gump, right? But I'm like the unimportant guy in the room in a lot of really important rooms where awesome things have been happening. And it's been great as a kid who grew up as a space fan to be actually able to participate in some of these things, notably to be standing, near the launch pad as Chandra went up on the space shuttle in 1999, and then to see the mission return, just, bonanza science ever since. So it's been a fun ride.
How is astronomy done differently now compared to how it was done maybe when you started your career?
Ooh, that's an interesting question. I mean, as I already talked about the move to multi-wavelength astronomy, so that's a big, an important change. If you were had a spectrograph and a telescope and you wanted to analyze the data, you basically had to write your own data analysis software from scratch, right? There weren't any of these software packages. And so the advent of the general user software packages, this layering of infrastructure in the field, the development also of the guest observer, that when you launched a satellite in the 1970s, the people who built the instruments got all of the data forever. So it wasn't like Hubble or Chandra, where a random astronomer around the world makes a proposal and say, I want 5 hours of Chandra time to look at this supernova remnant. That was something that came in with Einstein and IUE in the late 70s, early 80s. And so that transition to these user facilities, instead of the lone astronomer building their instrument and getting all the data from it, has really changed the field. And it's sort of specialized right into the people who support the missions and the people who, ask the science questions. There's a little overlap, but so that's been a real cultural change. Obviously, there's been an important demographic change. We're much less white male than we used to be, although more so than we should be. So that's also been, a really nice development in the field. But I think, that one of the consequences of these public archives of data as well. So not only do we have guest observers, but the data becomes public after a year. And so that means anyone can download the data. And that actually opens up some of these cutting edge data sets from Hubble, from Chandra, from these other space telescopes, and some now the ground-based telescopes are getting that way too. It opens them up to particularly scientists in developing countries who may not have access to actually, telescopes of their own that are of the same quality, but they can get this data and the software and contribute scientifically at the same level as the richer countries.
That's very promising.
If I put my Chandra management hat on, if you're an astronomer listening to this, right, proposal deadline is like March 15 or something. We take proposals from scientists all over the world. X-ray astronomy used to be this thing which was like, oh, we're the wizards. It's very arcane. You don't want to come here because only the special people can do it. And I've really been fighting to change that and make the software more accessible so that if you're an infrared astronomer who's never done X-ray before, you can still get Chandra data and get good science out of it. I think a much more collegial attitude to the field, a much more trying to make the barrier to entry lower is another good attitudinal change that I think we've had. Then there's the science change, right? Which is when I started off in the 80s, there were these big questions that we thought we'd never be able to answer, that have now been definitively answered. So, and these are questions, one of the great things about astronomy, right, is they're questions that we've had for literally thousands of years. How old is the universe? So when I started, there was like factor of 2 uncertainty, right? And now it's like 13.7 plus or minus 0.1 billion years. Done. Next question, please. Right? And, Giordano Bruno and the multiplicity of worlds. Is there, are there other Earths out there in some broad sense, right? And it's like, the answer is yes, almost every star you see in the sky has an Earth-sized planet. It may not be very nice to live on, but it's a planet that's like not completely different from the Earth. Done. Next question, right? And so, the fact that, science, right, used to be called natural philosophy. I like not to lose the fact that it has the origin that we are ultimately asking what used to be considered philosophical questions and answering them. And that's really where it's at, right? So I think I feel very privileged to have lived at a time when not only did I live through seeing the first humans walk on another world, but where we got to answer these really deep questions about the origins of the universe and the multiplicity of worlds and things like that, that were, that people have been asking for millennia.
Wow. So how do you see astronomy being done 30 years from now? Feel free to pick your time frame, but in future.
I mean, the next 20 years, right, we're already building, we're already designing instruments for 20 years from now. So it's not going to be that different is the problem, right? I mean, some of the science questions will change. And that's one of the great things, right, is if you'd asked me 20 years ago what are going to be the questions, I might not have anticipated the explosion in exoplanet science, which is really, but technologically, yeah, I think on a 40, 50 year time scale, right, we are going to move astronomy more into space. We're going to have to, because low Earth orbit's going to be so industrialized, we're not going to be able to see through the crap. And so, but on the next 20, 30 years, I think that we have a problem because there's, we have like the James Webb about to go up. We have WFIRST down the path. We have these big flagship missions that, frankly, in my opinion, are soaking up way too much of the budget, and the equivalent is true in ESA as well to some extent. And the problem is that there's a tradition in like particle physics, right, that you all work on the one big project, like the Large Hadron Collider. But in astronomy, there isn't one big question. There's a lot of little questions. And so traditionally, there's been a lot of different instruments working on these little problems that build the tapestry. And that's, I think, healthy for the field. And we're in danger of losing that because the funding selection processes are kind of constructed to drive. The answer is always, what's the top priority mission? And the answer is always going to be the top priority mission is the most fantastically expensive one you can imagine that can just fit within the entire budget, right? and so unless we kind of retweak the rules to say, no, give me a portfolio of missions and compare that against the one big mission, we're going to lose a lot of these little missions that have, like the WMAP mission that did the microwave background was a very small mission, comparatively speaking. And in Europe, right, France's Corot mission for exoplanets, was a really nice mission. And you want to make sure there's space for those. So that's what I'm most worried about, is keeping a space for those small missions. And and also I think a big change has got to be, we need more, and this is talking about my own salary here, so I'm not disinterested, but we need proper funding for the software. And the problem is there's still a feeling at the high levels that the software ought to come for free. That it's stuff that scientists should write in their spare time. And that doesn't really work for the big projects, right? And so, and when I say software, I'm including also archives and things like that. Proper archives with good metadata and proper data analysis software is expensive. And it's like comparably expensive sometimes to the telescope, right? In the long run, if you're talking about a 10-year use or something like that. And so we have to get past you can't spend that much money on the software and the archiving, because we're seeing in the results of the papers that are coming out how much that enables this serendipitous science, this follow-up science, this survey science that really gets the maximum out of the hardware investment that you make.
Astronomy research as of now is mostly publicly funded, right? Do you see a future where there might be any commercial interest in astronomy, in funding astronomy?
It's hard to make a profit from astronomy in under a century. It's not something, so much of the technology we have nowadays owes to people like Galileo and Copernicus or whatever, right? Well, maybe a little less than that, and that some of the stuff that astronomers were doing in the early 20th century, has effects on technology now. But it's not something that you get a 5-year turnaround for investors on, for the most part, right? And so I think ultimately it is a government-funded or occasionally rich person-funded activity. And it's an investment that has spin-offs. I like to think of it as, it's like art, except it actually does generate profitable spin-offs for the world in the long run, which is not to diss on art, because it's worth funding anyway, even if it doesn't make spin-offs. A lot of early photography came out of astronomy, right, for example, right? So there definitely are, there are things at the margins that are profitable. Well, for example, the space tracking is essentially astronomy. These are essentially doing astronomy in a different way. There are lots of examples that I'm not remembering right now. A lot of communications technology came out of early radio astronomy. Sensor technology, and it's a way of pushing the state-of-the-art of technology without blowing anybody up, which is the other way. Yeah. That kind of technology, right? And so in that sense, it's a good thing to invest in. But fundamentally, we invest in it because it's cool, because it tells us more about where we are, the discovery in the 20th century that we are made of stardust, that we know where the elements come from. That's worth having. That's worth a lot, I would say, even if you can't put it on the stock market. But yeah, I don't see commercial astronomy as being a driver at any point in the future.
Yeah. The human origin story, right, essentially is invaluable.
Yeah. But, where are we? What are we? Yeah. Where are we going? What are the existential threats to humanity, right? Even if the answer for asteroids ends up being, actually, the probability of a killer asteroid in the next 1,000 years is pretty low. The fact that we now know that is, okay, that's a good answer to have. and it's not zero, so we should still worry about it. What's the danger that the supermassive black hole in the middle of the galaxy will send a lepton jet our way and fry the entire spiral arm? It's like knowing what's next door. Knowing who's misbehaving next door is actually kind of important, right? So I think that's an ongoing, perfectly fine justification for investing as a relatively small amount of our GDP, right, in astronomy. Even if you include the space program, it's pretty small potatoes, and it's worth putting a little bit of what you have into these big questions.
I have a weird question. So what's your favorite science fiction? Because a lot of my astrophysics knowledge comes from a lot of science fiction. So
I'm a science fiction fan from like 3 years old when I started watching Doctor Who.
Okay. Wow.
So a lot of, in fact, looking back on it, way too much of my values and so on come from that show. But I remember at a small age also reading Le Petit Prince, Saint-Exupéry, which is, the little kid who lives on the asteroid. And,
yes, The Little Prince. Yeah.
Yes, yeah. And then, more after that, a big influence was 2001. Still my favorite. It's still the best movie ever. In terms of writing, I mean, I grew up on the, in my generation, right, it was Clarke and Asimov and Heinlein, and particularly Arthur C. Clarke, I think had a great way of making you think about these deep questions. I have like bookshelves of science fiction just behind the computer here. So, it's, I could list many authors that I love, TV shows and movies. I think Babylon 5 is one of the all-time greats. I have to give a shout out to that. There's sci-fi that inspires me, that makes me think deep questions. You go, well, why couldn't you do that? I mean, even in Star Trek, right? Which Star Trek movie is it where Picard goes to, it's the one with both Picard and Kirk. They go to stellar cartography. They go, oh yeah, what happens if you move this star here? Will that affect the motion of the cosmic string? And I'm like, okay, I want to spec that right now. We need that software.
Wow, okay. I didn't know this also works the other way around, sci-fi inspiring astrophysicists. So that's cool.
How do you think we got flip phones, right? No, absolutely it does. And because it's play, right? Play lets you take your normal ideas and stretch them in different directions and see where they break. So yeah, I absolutely both a fan of science fiction for its own escapist value, but also for the more, I have pretty lowbrow taste in it as well. I'll watch all the crap, but I also appreciate the more philosophical ones that make you think about the big questions, and that is the feeling you get from some of them, right, is similar to the feeling you get when a major new astronomical discovery is made. The kind of the sort of, holy crap, every galaxy has a supermassive black hole in it. The realization that went through the community, 15 years ago or so. Yeah. And that was that kind of big reveal moment, like in a movie. So it's very much, it plugs on the same heartstrings.
Wow. We also hear, or at least I heard, that a lot of astrophysicists make a good career, or they pivot well into finance. Is this true?
It is. I'm an exception. I can't, every time my financial advisor tries to, explain my retirement stuff to me, I glaze over. It's just like, it's like what other people look like when I try and explain general relativity to them. But I have a number of colleagues who left the field and went into, become quants on Wall Street and made ridiculous amounts of money. What astronomers are trained to do, right, is figure out how to answer questions that have never been answered before, that don't have an existing answer, to model things quantitatively in the presence of uncertainty. So we're not like solid state physicists who have really control of their experiments and, can measure things to the last decimal place and they can tweak a knob here. We can't tweak a knob on a quasar, right? And so we have, and our data is noisy. So it's actually, in that way, kind of similar to sort of economic data in that it's crappy, and we have to figure out what can we really know in the presence of crappy data, right? And so I think that makes us well matched to that kind of job. Not for me, but yes, they did a study right on the unemployment rate among astronomers. And, the people who started off in astronomy, a lot of them weren't in astronomy anymore, but none of them were unemployed. I had one friend who went to work for Legendary Pictures doing some kind of quant stuff on marketing, or something like that. People in all different kinds of works of life where technical skill is important. Another guy went to work as a statistician in Las Vegas. The one way to make money in Las Vegas is to work for the house.
Yeah, of course.
So yeah, it absolutely happens. And occasionally we get someone come back, offers to build us a new wing or something for that, so that's nice. There's this guy I knew in college. He didn't end up as an astronomer, although he was interested, but he was going to be like a computer guy. He really screwed up his exams. He spent way too much time on the computer playing, writing games and things like that. And so he ended up a couple years out of college, even though he got a bad degree result, as I recall, writing a program called FrameMaker that became major early word processing program that got sold to Adobe or something. So now at the observatory in Cambridge, there's a wing named after him. Damn, I was friends with him. I wish I had stayed in contact, but it's kind of a bit lame now to kind of go, hey, mate, remember me, 1980? So stay in touch with your geek friends because they might get rich. So me having had, not become rich, but having been rich in experience and adventure, intellectual adventure, having spent time standing on top of Mount Hawkins in the dawn after an observing night, seeing out in the desert, or watching the shuttle go up with my telescope on it, or these are experiences that I only dreamed about when I was a kid, and to have actually had them has been great.
Staying in space, not just astronomy, right? The space sector in general pays very little. So the ones who actually stick to the space sector have to be too obsessed with it and not be at peace working anywhere else except the space sector. So yeah.
Right, unless your name is Jeff Bezos or something. Yeah. That's right. Well, that's the old joke about space, right? Is the way to make a small fortune in space is to start with a big.
You mentioned previously that you like to follow the Indian space program quite closely, or you have been following the space program quite closely. So what really interests you in the Indian space program?
Well, to be fair, I follow all of the space programs, but I do have a soft spot for the Indian program. I think what was very interesting to me historically about the Indian program was that until about 15 years ago, it was very different in that it was not focused on the spectaculars. It was focused on the poor people of India. Right, that it was okay. We need weather satellites to predict the monsoon. They did with NASA the very first direct television broadcast from Geo to poor villages in India to beam educational information about sanitation and so on. Right, and so that focus on let's really see what space can do for our people, I think really set it apart. And obviously, there was a military side to it as well, because it was funded partly, to let the DRDO end up with Agni and things like that. But there was really this focus on, we know we're a developing country and we want to use space for the good of the people and not just for our prestige. Now, about 10, 20 years ago, India woke up one day and went, oh, we're a superpower now. We're rivals with China. We should do the prestige things. And ISRO switched around to do, Chandrayaan and now the human space program and things like that. And so it's like completely different now. But and that's okay. They're still doing the other stuff, and it's very impressive what they've managed to do. But I think that early success, and I contrast, for example, India and Brazil, which started trying to do space at about the same time. And Brazil never quite got there, right? It never quite managed to launch anything into orbit. It just sort of sputters along at a low level. India put the effort in, kept trying, got it right, and now has a world-class space program. So that's when you see how you can do it wrong, if you like, no offense to Brazil, I mean, there are reasons, political reasons why, but, seeing that really makes you appreciate how India did it right. Kudos to Israel. It's done a lot with a little.
What skill set is needed to get into astronomy or astrophysics?
If you're going to be good at it, you need some math. But, a lot of the people who got really high scores at undergrad didn't do so well in grad school. There's something else you need. You need, for a start, a lot of what you need actually is persistence. Perseverance is the word of the week. And you've got to pick away at things that are hard for, until they finally give. And so I think stubbornness is a key trait. And just being able to visualize things on different scales, maybe that you're not normally used to. So a good abstract mind. I think for any PhD in the sciences, but particularly astronomy, you've got to be able to work through the frustration of the thing not working for the 10th time. And actually, we make it work on the 20th time or something like that. So I think that's what I notice about the people who are successful.
It seems to be the usual path for astronomers, grad school and then PhD.
Oh, that's right. Like in aerospace engineering, for example, a master's is all you need. In astronomy, a master's is nothing. A master's is a dead end. Well, it's not dead, but it's like, there's no promotion path from that. It's a PhD or nothing in our field, really. And what I find is, having with students for many years, and if you do a master's, what that teaches you is to answer the questions that have already been, to know how to find the answer to questions that have already been answered. And the PhD tells you how to attack a problem that hasn't been attacked before. And it also is, in a PhD, you go really deep on one problem. And so you know where bottom is. And so when you attack the next problem, even if you don't go that deep, you understand that you haven't gone that deep. You know how far you are from bottom, right? So you know what to believe and what not to believe. Whereas I find people who don't have PhDs often think they've hit bottom when they haven't, if you understand what I mean. So it's that experience of really exploring a new area and exploring all its ramifications down to the deepest level helps you understand what solving a problem really is. And then that helps you do the kind of half-assed job on other problems.
There's a lot of instrumentation that's required in the area of...
Absolutely. So within astronomy, right, some people specialize in instrumentation and do a PhD in that. And so building a new instrument and getting it to the mountain and getting minimal data on one object, that's a PhD. And that's a very marketable one because both within astronomy and also out in industry. I ball thumbs, I couldn't do that. I'm much more on the mathematician end of the spectrum, the screwdriver end of the spectrum. But yes, we very much value those people. And so, so there are instrumentalists, there are observers who maybe don't have the same math skills I have, but are really good seeing what question to ask of the sky, and setting up. A very important skill, by the way, is grant proposal writing and observing proposal writing. So even if you're not asking for money, you're asking for time on the telescope. I also suck at this. Is writing proposals. I hate, but it's what we spend a lot of our time doing. Persuading other people that the science you're gonna do is going to be great. and that if you give me this time, I will be able to answer this question with this level of accuracy. It forces you to think through. It's not just, oh, it would be cool to look at this, right? It's like, with this camera, I can get this sensitivity and this spectral resolution, which means that even if the star is not flaring, I can set an interesting limit on how much it's not flaring. Even if I see nothing, I will have learned something. That's the test of the good proposal. And so you have to be able to work through these things quantitatively and simulate what you're going to see and understand what's going to screw you in the quirks of the instrument. Actually, like often 90% of the work in a project is done at the proposal stage. And if you've done the proposal right, the data should be pretty easy to deal with, but it's never quite that. So that's a lot of what we do. And so actually another really important skill comes out of that is communication. A lot of people in the hard sciences don't appreciate how important writing and speaking are, because If you haven't published your results, you haven't done science. If you haven't explained your results to someone else, you haven't done science, right? And if you haven't persuaded someone that you should be given the telescope time, then you're not doing the science in the first place. So, things like grammar and spelling are still, a good foundation. So I think those humanities skills, if you like, are also important in the sciences and in astronomy in particular.
Do instrumentalists also require a PhD?
Yeah, if you want to be principal investigator on something, right, you probably should have a PhD these days. And so I have a friend who did her PhD on building part of Spitzer. That was her PhD, was building part of the Spitzer camera. I have a couple of friends who did that, different bits of Spitzer, and one of them is Amy Meinzer, who's now head of the NEOWISE mission that searches for near-Earth asteroids with this infrared space telescope. So she's a senior person at JPL, but she started off doing an instrumentation PhD. Pauline Barmby, who's now a professor in Ontario, there started off also building a different bit of Spitzer. The promotion path, even from the instrumentation side, is if you are a PhD scientist, then you get to be the leader, where you get to decide what your next project is as a scientist. You pose for it yourself then. If you have a master's, you may be a research assistant in a group, but you're not going to be the person who decides what work you do. For me, that's the key freedom, right? Is to have a certain amount of freedom in deciding what your science time is used for. So I have to spend, 60, 70% of my time supporting the Chandra mission, but I have a 30, 40% of doing my own science. And if I didn't have a PhD, if I only had a master's, I wouldn't have that freedom.
Yeah, now I understand why in the Big Bang Theory, the sitcom, the others make fun of the guy who doesn't have a PhD.
Oh, yeah. And, I can't watch that show. It's too painful because I'm like, how did they get a video camera in my dorm room? It's just way too close to the book. I only watched the first few episodes and then I just couldn't deal with it anymore. But yeah, I know those people. They were me and my friends. More seriously, if representations of scientists, right, in the media are usually pretty bad. One of the notable exceptions was Contact, where they really captured what scientists are like. I thought, you can see Sagan's influence there, but both in the hero moments for Ellie Arroway, but also, the asshole advisor, Drumlin, right? And the slobby graduate student. And, these are people that I can all see meeting at AAS meetings, whereas, it's such a refreshing change from Christopher Lloyd in Back to the Future as the mad scientist archetype, right, is what we're usually represented as. So, yeah, it's nice when you get representations like that.
Yeah, that was one fantastic movie. Do you, by any chance, also have a backyard telescope that you like to get out from time to time?
I did have when I lived in England. We have a 9-inch refractor at Harvard. In non-pandemic times, I have access to, and I train the other scientists to use it. And so this is a 100-year-old telescope that gives beautiful views of the Cassini division in the rings of Saturn and things like that. So that's what I use when I want to, revisit my amateur astronomer life. From the center of Harvard Square, you can see bright planets, but you can't see much else. The light pollution here is pretty bad. But I do I have been known to grab random strangers off the street and go, have you ever seen Saturn through a telescope? Follow me. This stuff is out there. It's right there in the sky all the time, and you don't notice it. And so, just showing people that it's there. That's what blows my mind about just looking at Saturn through a refractor, right? Is that if you had slightly sharper eyesight, you could see it looking like that all the time. Yeah, you're just holding a magnifying glass up to the sky, but it's there all the time looking at you, and that is this ridiculous looking thing. It's easy to show people, yeah, you should really be excited about this because just look. And I think for me, one of the big realizations, right, was really understanding when I got into the physics, how you start off with simplicity and complexity emerges in this very natural way, right? That basically you have a very smooth, simple universe defined by a few numbers. And the fact that gravity makes things curdle and quantum mechanics makes things get hot means you just have to simmer and stir for 13 billion years and you get us. And that the way that emerges so beautifully and naturally gives you an understanding of how the world works that I find so much superior to the idea that, some magic guy up in the clouds went zap. And it's really a beautiful story, the story of what E.O. Wilson calls consilience of science, the way that it all hangs together and make this story that actually explains in broad features the features of the everyday world that we live in and how it got there. And that the fact that one of the things I do in the history of science, right, is I see the history of humanity as basically, we don't understand, it's all magic. And then between 1850 and 1950, it was like, oh, okay, that's how it works. And now, there's lots of science still to do, but we basically have the idea now. And I think that was, we talk about science as this sort of slow path, but I think it was more a step function. I think there was a couple of generations where humanity finally went out of the magical thinking way of the world and figured out what was going on, what atoms, what elements are, what chemicals are, what light is, what planets are, what the universe is. And it just all came together in this very short space of historical time that our culture is going to take a couple hundred years to catch up to.
I always keep wondering about if we are going to ever make contact with other sentients. So, what's your take on this?
Take the Drake equation, right? And we've been knocking down the terms in the Drake equation. And the big thing is this number, e to Earth, that the fraction of stars that have planets like Earth, basically, is high. And so that's super good news for the probability of life elsewhere. The probability of sentient life, the more we understand about these exoplanets. For example, I've been recommending to people this great book by my colleague Elizabeth Tasker called The Planet Factory, which talks about all the different exoplanets and how they'll kill you in different ways. We're learning all the different ways that the planet can be really bad to live on and not be friendly to life. And so it's clear that there are all these Earth-sized worlds out there, most of which are very hostile. And so still the sheer numbers, right, say that there must be other worlds that are nice. Always the question is life as we know it. In general, what you need for complexity, a certain amount of stirring, but not too much, right? A certain amount of energy input, but not too much, right? In just very basic physics, if it's going to be very hard to, life is, how we define life, right? It's got something to do with information processing, especially sentient life, right, is information processing. And so it's hard to do information processing in the center of a star, for example. It's a little too hot. The patterns don't stay fixed enough. And it's hard to do it in a very low density, cold environment because not enough is going on. And so there are, I think one can argue bounds on whatever we think life is. Can set bounds on the sort of environments that might sustain complexity enough for life. I mean, one of the big questions maybe is timescales. Like maybe in a more energetic environment, entire civilizations are born and die in a nanosecond. Can you live that kind of complexity? So timescales are always important in astronomy. I think the best guess right now is that the universe is full of some level of life, that there are other sentient civilizations, but they're a long, long, long way away. Maybe not in this galaxy at the moment, but probably we're not the only sentient civilization to have existed in this galaxy in the last few billion years, right? And so the one thing that science fiction movies always get wrong, for the most part, right, is the time scale. If I walk out of the house and the first person I meet is not only the same age as me, but was born on the same day in the same hour, that would surprise me. That would be unlikely. And the equivalent is the first aliens we meet are, within a million years of our own level of evolution, right? That's not what you expect. You expect them to be tens to hundreds of millions of years behind us, in which case they're not interesting, or ahead of us, in which case they're like gods, right? But not at the same level as us. Just because of the timescales in the galaxy, it would be really coincidental for them to be at the same sort of level of development. And so I think that's one of the challenges.
Speaking of life as we know it, there's this amazing science fiction book called The Dragon's Egg that talks about talks about life that evolves on a neutron star.
Yeah, so that's an example, and again, the timescales were important there, right? The nuclear timescale was very different from the electromagnetic timescale, and so yeah, that's a nice example. And Ford, of course, did a lot of space technology prognosticating as well. He was a very interesting guy. Yeah, so no, that was a nice book for sure.
If any space enthusiasts or students or young professionals want to reach you, what's the best way?
Yeah, just tweet me is probably best. Planet4589 on Twitter. That's where I hang out a lot.
Thank you very much, Jonathan. It's been an amazing talk. Never did I think that I'll be talking so much of science fiction, actually, with a super cool astronomer. So a lot of things you've given me to think about.
Really nice to actually get to know you a bit, and let's talk again sometime.